Good morning, everybody. Welcome back to the first day of the rest of your life. We need to talk about magnets. Yeah, we got this. And I know I've been alluding to how hard this stuff is, and it will get hard, right? But in physics, hard usually means fun. You'll come around to my way of thinking, I think. Maybe. We'll see. But physicists, we tend to get like, I don't know, scientists are weird, and you know this. You're becoming one, and so you're probably weird yourself. But geologists, I'll just pick on geologists for just a second, give you an idea of what's going on here. I've never seen somebody get excited about a natural disaster the way a geologist does, right? Some horrible earthquakes happened somewhere. Some volcanoes erupted, displaced all these people, and a geologist is just sitting there going, oh, it's a volcano. Oh, that's so bad about those people. Oh, volcanoes, right? Physicists, we tend to get really excited about things that are really hard. Not because they're hard, but because they're interesting. Like, it's no fun if the ball's just sitting there. We want to throw it, we want to launch it, we want to bang into stuff, right? And that gets harder, but it's more interesting. And magnetism is electrodynamics. We've been doing a little bit of electrodynamics, the movements of charges and things. And magnetism builds on all of that. And so what we're going to do is we're going to try to start at the very basics of magnetism, dealing with single charges being influenced by magnetic fields and kind of build from there. Just like we did back with electric fields, right? We started with electric forces, and then we went to the electric field, and then we went to voltage, right? We're going to try and do very similar process, but I do have to stop a little bit and point out that even though most of the pictures I have on the screen right now involve permanent magnets, I'm actually going to save permanent magnets for the very end of the semester. Permanent magnets require a little bit of quantum mechanics to be able to talk about. And so I'm saving them for the end of the semester as a bridge for those of you that are going into Physics 4C, okay, as a bridge moving into that. If you've had Physics 4C already, you already know the punchline, and so you can just sit there with a smug look on your face. But just to point out that I am kind of sweeping under the rug right now permanent magnets, like refrigerator magnets, right? Not going to really talk about that. And even though we're going to play with bar magnets and things like that in lab next week, we're really not going to explain why permanent magnets have the magnetic fields they do. We're going to measure the field, we're going to interact with the field, we're going to do all that kind of stuff. But we're not going to explain why. Okay? We will explain why, not this chapter, but next chapter, we'll explain where one source of magnetic fields, currents. But we'll save permanent magnets for something else. Okay? Magnetism historically is the force that we've known about the longest. It was kind of well understood even before we understood gravitational forces, originating way back into antiquity. Shepherds, people that, so back in the olden days when they were chasing the sheep around the hills, oftentimes they would have a staff, and to protect the ends of the staff, they would put iron caps on the end, just kind of, wear and tear, that kind of stuff. And these ancient shepherds would notice that there were certain rocks that would stick to the iron of the ends of their staffs. The story goes that one of those shepherds was named Magnus, and that's where we get the root for the word magnetism. I don't know if that's a true story or not, but it's a cute one, right? And involves sheep, like just about everything does. We know today that the Earth's magnetic field protects us from the radiation of the sun. The magnetic field is one of the reasons you're able to enjoy your day today. That we can be together talking about physics. Blame it on the magnetic field and Ben Franklin, right? All that kind of stuff. But we need to talk about these fields. And I want I want to get something out of the way right now when it comes to magnetic fields. And unfortunately, all of my demo equipment's over at the old building. So we're just going to have to make a digital version. And it's not going to be all that great anyway. But let's see if I can get this to show. You guys see my compass on my phone, right? So even though it's a digital version, it's still using a sensor here to sense the magnetic field, okay? And we'll talk about how that sensor works later. We get to something called the Hall effect. But as you can see, I can rotate my phone around, right? And I can line up my phone's direction with the north direction, right? Okay, so roughly that way over there, okay, is magnetic north, right? Now, I know you know something about magnetic fields. That magnetic fields have two ends, so to speak. What are they? North and south, right? So we're going to get into how a magnetic field is a dipole and what a dipole is and all that kind of stuff here in a second. But at its basic, a magnetic field consists of a north pole and a south pole. And there's rules about the north and south poles, aren't there? What are the rules? Opposite attract like. Okay, so it's starting to sound a whole lot like electricity, isn't it? Okay, so notice how no matter how I rotate my phone, okay, that do you see how north always stays pointing in the same direction, right? So that part of my sensor is being drawn that direction. So if this were a bar magnet, and it kind of effectively is, okay, that north pole of the bar magnet in my phone points which way? Okay, let's standardize here, okay? And we'll not go straight magnetic, we'll go true, okay? So Santa Claus lives that way. Yeah. Santa Claus lives, right? Okay, we good? We good, Lewis? All right. Penguins are that way. We good? Okay. The sun rises over there. Lewis, you're killing me. The sun rises in the east, right? Okay. And Japan is that way. Yes. Are we good? No, Japan's to the west of us, across the Pacific Ocean. Big revelations for Lewis today. Okay. Santa Claus, penguins, sun rising, Japan. We good? Okay. Which way is this? It's north. It's north. The north end of my now blank phone. Okay. The north end of the magnet in my phone is pointed that way. The north pole is pointing that way. So what kind of magnet's over there where Santa Claus lives? A south pole. Okay, wait. Where does Santa Claus live? At the North Pole. Why is it called the North Pole? Because the North Pole of compasses, which are magnets, point that direction. But in order for the North Pole of a magnet to point that way, what must that pole be? A south magnetic pole. Okay, I did it. All right. Yeah, okay. So, hopefully I've established for you the idea, the truth, that the place where Santa Claus lives, known as the North Geographic Pole, is in fact the Earth's south magnetic pole. And how do we know it's the south magnetic pole? Because the North Pole of all other magnets point that way, right? And you just told me north and south attract, right? Okay. So the place where the penguins live, the south geographic pole, the direction which the south end of all compasses point, must be a what? North magnetic pole. So the magnetic poles of our Earth are opposite what we call them. I'm not in charge. Because the north end of a compass points that way, and that's kind of an easier way to say that direction is north.
So this is a conceptual question?
Very much.
The north end is going that way because of the south pole of
There you go. Got there in the end. All right. Okay. So, and then Rose brings up that they switch. That north becomes south and south becomes north. And that is true. That happens once every million years or so. There's geology, there's big error bars on it. So it happens as quickly as 1,000 years, but it happens as long as like 10 million years. So somewhere in between 1 million years or so, north becomes south, south becomes north. And the last time this change happened was about 1 million years ago. Yeah. So, what? Well, over the period of about 1,000 years, it'll flip-flop and then it'll settle down. The reason this flip-flop happens is complicated, but it comes down to what we're going to learn next chapter, where moving charges create magnetic fields. There are moving charges inside of the Earth. The Earth has a molten core, and there's nickel and iron ions down there, okay? And those charges move around, but they can change the directions of their flows. Currently, we are seeing a weakening of the Earth's magnetic field. We actually have almost 180, 190 years of magnetic records, thanks to the British Royal Navy, who took like crazy recordings of magnetic field direction and strength in all of their boats over the years. Going back to the times of the great explorers and all that kind of stuff. But the the south magnetic pole of Earth has been shifting. It was somewhere in the Arctic Ocean, and now I think it's like moved slightly towards Russia, and then it's kind of moved away, and it's been wandering around. The Earth's north magnetic pole actually isn't on Antarctica at all. It's sitting somewhere in the I think it's the Atlantic Ocean, somewhere between the Atlantic Ocean and the Arctic Ocean. Antarctic Ocean, sorry. So they're a little bit offset from the actual rotational poles of the Earth. The Earth's rotating and its axis is tilted, and we know that axial shift. So here in California, that's magnetic north, but true north is about 15 degrees off. And when you're flying airplanes, you need to make those corrections. It's kind of important. But to Girk's comment that almost nobody heard, GPS will be unaffected by this because GPS could care less about magnetic fields. So even though the magnetic field is weakening, it'll get weaker. Cancer rates will go up slightly, but it'll still be less than the other things we're doing to our bodies to give us cancer. And then we will still be able to navigate because GPS is totally independent of magnetic fields. So, sure. Although everybody's bringing their phone and has GPS in it anyway. All right. Let's talk about magnetic. Okay, so I am going to draw a bar magnet because it is the easiest thing to sort of attach our brains to. Okay. And I'm actually, let me flip the directions of those poles right there. Let me put the north end over here and the south end over here. Okay, so this bar magnet makes a magnetic field. If you've ever played with a couple of magnets, you've felt the force of interaction between these fields. So like we had for electric fields, there's rules for thinking about these fields, drawing the field lines, all of that sort of stuff. So we're going to carry all of that language over that we had for electric fields into magnetic fields. Only the key difference between electric fields and magnetic fields is that electric fields start and stop places. Where do electric fields start? Positive charge. Where do they end? Okay. In magnetism, there is no start and stop. Magnetic fields always form closed loops, even if you're drawing it out to infinity and coming back around, okay? There is no positive charge in magnetism. Long predicted as being in the math and theory of electricity and magnetism is this idea of a magnetic monopole, meaning like a north pole all by itself and a south pole all by itself. We've never been able to make or detect the presence of a magnetic monopole. That is instant Nobel Prize for anybody that gets one. But they just don't happen. Magnetic fields always come as pairs, north and south. It's called a dipole field. We skipped the dipole back in electric field because it wasn't that important back then, but it becomes important now. And a dipole field has these characteristics, okay? We are going to define, we're just making a call here so that we can all speak the same language, but we're going to say that north poles is where magnetic fields emerge or come out of or come away from, okay? So in the case of this bar magnet, I'd have a magnetic field line that would come out of my north pole, loop around, and go into my south pole. Now, typically this is where the drawings in textbooks and the internet kind of stop, right? They'll indicate sort of the direction that these fields are going with arrows, and they'll kind of imply, right, that they're starting on the north pole and ending at the south pole. That is not what happens. These field lines continue through and close off the loops on the interiors of the magnets, okay? So first rule, magnetic fields always form closed loops. There is no start or end to a magnetic field line. It's going to close on itself eventually. Now we can depict other field lines coming out of here, right? We could say that they do that, right? As long as we draw the equal number coming back from infinity and going in, right? How many field lines could I draw? An infinite number, right? But we draw a representative amount. The directionality of that field is away or out of north and then going into south, but that, again, just gives an orientation to the field. So we're going to be working with dipole fields, right? These looping fields as they go. And what we want to be able to do is be able to do complicated arrangements of magnets. So like, for example, if I brought two, well, what happens if I bring a north pole and a south pole together? You know that they want to come together, but what would the field, the magnetic field lines look like here? North, what happens at a north pole? Comes out, but then what does this field line want to do? It wants to go into south, right? So we get a field between these magnets that looks like that, wouldn't we? And what happens if it's a north and a north, or a south and a south? They would repel, right? We'd have fields that are kind of doing that. And you notice here how I didn't finish the loops here. It's like these ends don't exist over here, right? I can draw like just a field in a certain location. I can like say, okay, in this part of the page, I have magnetic field that's all pointing this way. Okay, well, if I draw that as my magnetic field in this region of space, where's the North Pole? It's got to be somewhere on the left, right? And where's the South Pole? Somewhere on the right, right? Like the directionality of the field tells you goes from north to south. Okay, what happens if we cut this magnet in half? Get two magnets. Like that. And the magnetic field lines would just continue, right? They'd still go from north to south, right? Okay. Well, what happens if we cut those two? We have two more magnets. Well, four now, right? South, north, south, north, south, north, south, north. I'm going to get tired. How many? Okay, we cut all these magnets. What do we get? How far do we go? Well, we can't go infinitely far because we can get down to what? No, not infinity. You guys have been going off about him the entire semester, and I've been telling you to forget about him. You've successfully done it now, and then I can't. Now I got to bring him back. What was it? I heard it. Electrons. Infinity. It's not infinity. The smallest thing we can, chunk of material is the electron. And guess what the electron has? It has a magnetic field. It's got negative charge, but it also has a north and a south pole. Like charge and mass, magnetism appears to be, for all of our looking and all of our theory, a fundamental part of what makes up stuff in our universe. Mass, charge, magnetic field. Okay. Now, of course, we have structures in our universe like the neutron, which doesn't have any charge. Okay. And we have other things that have neutral or seemingly very weak or small magnetic fields. But by and large, just about everything, get right down to it, right down to the fundamental properties of what makes our universe: mass, charge, magnetic field. All right. Just to give you a preview of what's about to happen, or next chapter, really. What happens if I drop another, say, magnet right here? Yeah, what will the red magnet? Let's say we put the red magnet's a compass, right? Like a compass is a bar magnet that can swivel. Okay, so which way would this thing swivel? Yeah, the north would want to go that way, and the south would want to go that way, right? What causes things to rotate? Starts with a T, rhymes with orc. We're bringing torques back? Does anybody want to quit now? Yeah? Counselors are standing by. 4A, do you remember torques? Trying to forget them, Mr. Balogh. Really? You're bringing that back? Yes. Now, it's true that red bar magnet experiences a force, but more correctly, it experiences a torque, a force that would cause it to rotate into the orientation that would follow those magnetic field lines, aligning its own field lines with the field lines that are around it. So we are going to have to talk about torque. Don't worry, I got you back. We'll review a little bit when we get there, but it's another one of the reasons this can be rather difficult. Okay, all right. So let's before we just start really freaking you out, okay, let's talk about a quiz. Forgot about the quiz. Let's talk about the quiz. So, having alluded to a lot of the complexity that can be here, it's time to give you some of the rules. And what we're going to do is we're going to back up. We're going to try and go pretty simple in terms of what happens when you have just a positive charge and it goes into a magnetic field. Well, it turns out that the force, so here's a charge, here's a magnetic field. The symbol, by the way, for magnetic field is B, capital B. M, capital M is reserved, and it's also too easily confused with mass. So we use the B as the magnetic field symbol. The units of magnetic field are Tesla. Also Gauss. You can use Gauss, but Tesla is the SI unit. The Tesla and Gauss differ. 1 Tesla is 10,000 Gauss. Gauss was originally used to measure the strength of the Earth's magnetic field, which is actually pretty low. And so rather than having to run around and say micro Tesla all the time, sometimes the Earth's magnetic field is just given in Gauss. And we'll get more into the units of Teslas here in a second. But this charge, if it's moving with speed v when it enters the magnetic field, will experience a force. This force is called the Lorentz force. It's proportional to the amount of charge. So however much charge you've got, it's going to be bigger or less, depending. The speed that the charge is going, and the strength of the magnetic field. Now, you'll notice I wrote the proportional to sign, and I left all of the vector signs off of these things, because what's a vector in here? Well, let's ask the question, what's not a vector in this statement? The charge, right? Okay, everything else, the force is a vector, the velocity is a vector, the magnetic field's a vector, but this is a proportionality. I haven't really talked about vector directions or any of that kind of stuff, right? So the actual Lorentz force, the force that a charge experiences when it's in a magnetic field, is equal to magnitude of the charge times the product of its velocity and its magnetic field. What's the only way that you can multiply two vectors together and get another vector out? It's via the cross product. All right. So, several things here that we have to unpack, right? Cross product being one of the horrors, okay? And remembering how to do cross products, right? Maybe we'll cover a little bit of that here. What else? What other horrors have we got here? Let's see. Well, an easy one is, what's the force on a charge if it's not moving? 0. The magnetic force on a charge is 0 if it's not moving. Okay, so this is a unique condition, right? For electric fields, there was no condition on whether or not the charge was moving, right? A charge is going to experience a force in an electric field no matter what. But a charge can only experience a force in a magnetic field if it's moving. And it's moving in a direction that is a little bit perpendicular to the magnetic field. Because what happens if this velocity is in the same direction as the magnetic field? What happens when you take a cross product of two vectors that point in the same direction? You get 0. So the velocity not only needs to be not 0, but it also needs to have a direction, some component of its direction that is perpendicular to the field. If it isn't, if it's totally parallel with the field, this charge again is going to experience no magnetic force. So we review cross products pretty quick? A little bit? Why not? So cross products. Okay. So cross products, let's see here. There's kind of two ways to do this, right? You can do the whole matrixy thing. A, Y, A, Z, B, X, B, Y, B, Z. Have you guys seen this before? If you took me for 4A, you saw this, right? What do you do here? Like if I want, so we expand this out, right? And the I hat component, like what do? Yeah, we cover that up, right? And then we multiply and then subtract off that one, right? Okay. So it's like an algorithm, right? BZ minus AZBY. You kind of know you've done the algorithm correctly if you're looking for I hat and none of the X components show up. And then the part I always forget, minus J. And when we do the J, we cover up the J column and we do our determinant again. Going fast here. If it's been a while since you've seen this, come find me later and we'll do some practice. BX right there. All right, plus K hat, and then what do? We cover up the K hat. We do our little 2x2. AXBY minus AYBX. There we go. So that's one way to pull off a cross product, right? If you know the components of your vector in three-dimensional space, you can do that algorithm.
Why do you add the k hat instead of the j hat? Why aren't they both negative or both positive?
When you do the matrices, you have to flip what direction you're going.
So
Because you have to go right to left.
so the question is, why is it negative j and positive k, and not the other way around or something like that? The answer I want to give you, the short answer is quaternions. Yeah, I know that didn't hit very well. I did not know the answer to that question until about 5 years ago. 5 years ago, I had a student come back. His name was Zach. He was a tutor. And he came to me from wherever he was, Berkeley, Stanford, I can't remember where he went. And he came back to visit me one day, and he had a big grin on his face. He walked into Grasp, and I gave him a big hug, and we were talking. He's like, Mr. Balogh, I figured out why it's negative j and positive k. I was like, really? Show me. 45 minutes later, I begged him to stop. Because we were doing n-dimensional vectors called quaternions. And it's actually pretty elegant and really amazing, but my brain got full. So the answer is it's complicated. And I've learned to live with it. I minus j plus k. Yeah. Definition of the cross product. Okay. Well, yeah, if you do that right. Anyway, I don't do it that way. All right, there's another way to find the magnitude of a cross product. Does anybody remember what it is? It's like magnitude of the dot product, but different. Magnitude of A, magnitude of B, sine, angle between them. The dot product is magnitude A, magnitude B, cosine angle between them, but the cross product is magnitude A, magnitude B, sine of angle between them. The only problem is that's a magnitude, right? How do you find the direction that that vector is pointing? By something called the right-hand rule. All right, we'll get there in a second. Let's go back to here, okay? Magnetic force on a charged moving particle. A cross product always gives you a vector that is what? Perpendicular to what? To both of the original vectors simultaneously. The vector you get out of a cross product has to be perpendicular to both of the vectors that went into it at the same time. Big words are the vector must be mutually perpendicular to the two vectors that went into it. Okay. So what that means is, if I have the magnetic field like I pictured here, and I've got to reorient my charge velocity. Let's say I've got the velocity going up along the positive y-axis. I have a magnetic field along the positive x-axis. There are only two directions that is perpendicular to both x and y. Which way is it? Z. In the way pictured here, it's either into or out of the screen, right? Because I've got my positive x-axis pointing this way, I got my positive y-axis pointing that way, and the only directions that can be perpendicular to the x and y at the same time is the z-axis. Do we have three-dimensional paper? No. Please, please don't ask me to draw in 3 dimensions. I know you're asking. Okay, this is not the way we do it, but this is the best I can do. What I tend to do is I tend to like orient myself on like some 3-dimensional plane, and then like we've got B, we've got V, and then F would be doing something like that. How'd I do? That's as good as it gets. It's all downhill from here. And it's very, very awkward, and it's not good for precise depictions to do it this way. We do have modern tricks, though. Like the ability to just upload 3-dimensional objects into web pages, right? And be able to spin them around, right? Okay, so this is kind of, well, in essence, it's 3-dimensional paper, isn't it? Okay, so, you know, one of these, like the green one could be my velocity vector, the red one would be the magnetic field, and then the blue one could be my force, right? This particular one, I can give you a link to this one if you want, but I think this one I also did. You guys okay being in a YouTube video? See if I can get it. Will it attach? Come on, attach. There we go. Oops. And it ended up being really big. Okay? But we can walk around this thing in 3D space, right? And see which direction it goes. I don't know why it attached the way it attached funny. But there it is, right? And I can walk around. Right? Okay? So these are the kinds of awkward like 3D pieces of paper we've got, right? Okay? They're not the greatest, but they do things, right? Right? Okay? All right. But we do have tried and true methods for doing these, okay? If somebody reminds me, I'll put that up on the website. You can see we can't see the URL. Do you see the URL up at the top? Mr. Balogh, spell out the Mr. M-I-S-T-E-R, .github.io /XYZ axes. There it is. Okay. So, oops, this one. So, how do we deal with drawing in 3 dimensions and simultaneously find a unique direction for our cross products? Because there's only one direction that force can be. We know, like in a cross product, the mutually perpendicular direction has to be into or out of the page. But the question is, which one of those is it, right? The answer is the one given by the right-hand rule. So let me see if I can't explain how to do both of these things at the same time. Here's like the standard method, okay, for drawing these forces, magnetic fields in a fake 3 dimensions. It's 2 dimensions, but we're faking the third. This is what we're going to do. We need to be able to draw, say, that vector heading into or out of the page. A vector is an arrow. And if I might be rather violent for just a second, if I'm up here with my bow and arrow, and I shoot an arrow at you, What do you see as the arrow comes at you? You see a dot, right? So, to visualize a vector that is moving out of the page, you just use a dot. Now, in books, they'll often like draw a circle around that dot. I don't do that. My dots get messy enough, and if I start drawing circles around them, it's gonna turn into a dumpster fire. Okay, but you just use a dot. Okay, if you are the one doing the shooting and you're watching the arrow go away from you, what do you see? You see the tail. You see the feathers, don't you? So into, you're going to draw that. This is how we are going to draw pictures in 3 dimensions. It gets pretty cool. Watch this. If I wanted to depict, let's say I've got, we'll go back to the example I had before. Let's say my magnetic field is that way everywhere in the page, and I have a charge that is moving up. The way that we find which direction it is, into or the force, into or out. Remember that the force is equal to, the magnetic force is equal to the charge times the cross product between the velocity and the magnetic field. We're going to use the right-hand rule. So the right-hand rule has an order to it, okay? And I like to call this the handshake rule, because if you're going to shake hands with somebody, how do you hold your hand? Right? You're going to come in, shake. We don't have to shake hands, but like, right? Like you're coming at somebody like, I don't know. Why do we do that? It's a sign of, look, I have nothing in my hand. I'm not going to kill you. Check for weapons. I kind of like how they do it in Asia. Just bow. Right? And then I don't have to touch people. Right? Okay? But you come in and you got your palm in a shape where your fingers are straight out, right? And your thumb is sort of extended, right? Because you're going to clasp hands. So you're going to start your right-hand rule exactly like that. And you go in, you point your handshake, your fingers, okay, in the direction of the first thing. In this case, the velocity. So which way is the velocity going? Up, right? So take your hand and you point your fingers, straight fingers up. Excuse me. Then you have been endowed with this amazing structure up here called a wrist, okay? And it can go in a lot of different directions, okay? So what you're going to do is you're going to rotate your wrist, sometimes your whole body, sometimes your whole arm, okay? You're going to rotate so you went up with your fingers. Now you twist your palm, your fingers around so that you can bend your fingers in the direction of the magnetic field. It goes velocity up first, and then fingers bend over in the direction of the magnetic field. Your thumb is now pointing which way? Into the page. V, B, thumb is now pointing into the page. That's the direction of the force. So how would we draw that force? As an X. Pointing into the page. We're going to do this a lot. We're going to do this a lot. Now, I taught you what I call the handshake form of this rule. There are other forms of this rule. Okay? Some of you may have been taught this by math teachers. Does this look familiar? Okay, the shooting, boom, 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 whatever. Okay, right? In this version of the rule, your index finger is V. The velocity is your middle finger, and your thumb is the force. Personally, because I'm old, I find holding my hand like this for long periods of time hurts, okay, with arthritis, all that kind of stuff, which is why I like to do the fingers and then bend, okay? Whatever you're doing with the right-hand rule, you should not be causing physical pain. Mental and emotional trauma is okay. But if you are dislocating your shoulder or like, there's a pain, it hurts, You're doing it wrong. Okay? Your fingers should naturally bend at 90 degrees, right? To go in the direction of the magnetic field, but you start with a V, right? This can be any orientation, but then your fingers have to be turned. You want your hand to be kind of in this shape when you're done. Yes?
What direction is that?
Use your right hand, Lewis. I know, I'm good. Okay, I'm just checking.
How? Okay, look, I get like forward, right there, right there.
Uh-huh.
What about like that?
Turn your body. The other way.
Like that?
Uh-huh.
You gotta do that.
Oh, it gets way worse. You're going to be doing this in public. You're going to be in the library or something like that, right? You're going to be sitting there, you're going to be going,
Just don't angle your head forward.
right? People are going to look at you like you are nuts. I had a, believe it or not, there is a magazine called the Physics Teacher Magazine. You can imagine how exciting that one is. It was on the back cover one issue that I thought it was great because the back cover had a picture of a bunch of students in a room like this, and they all had their right hands out and they were all doing, right? And the caption of the picture was, "Guess which country these students are from." The right hand rule is an internationally understood rule. Everybody, I don't care what nation you're in, if you're in STEM, the right hand rules are the same. And so the point of this whole picture and caption was you can't tell what country they're from, right? Because the right hand rule is so universally understood. There was a higher than normal proportion of redheads, so I just guessed like Scandinavia, and it turned out to be like Norway or something. My uncle, who is a geologist, went to Japan once to give some lectures on geology. And he was speaking through a translator. And the translator in one of the meetings was having a difficult time translating what my uncle was talking about in the geology. My uncle was explaining something about magnetic field and rocks and things like that. And my uncle finally, because he saw the translator was having trouble, my uncle was like, "Stop, just stop." And he turned to the 300 people in the audience and just went like this. It was a different right hand rule, okay? And everybody in the audience was like, right? Physics gang signs, right? Okay, is what these are, right? So the first gang sign I am teaching you, okay, the right hand rule, okay, first. There's a lot more. The electric fields versus the magnetic fields. Oh, geez, we shouldn't make jokes about that. All right, so let's practice a lot here. Oh, by the way, there's another variant that uses the palm. Has anybody seen that one? Okay, you'll run across that one. You'll run across that one on YouTube a lot. Okay, it's used. I see it used a lot more in Asia, where like they'll say like the palm is the velocity, right? The stretched fingers and the palms. Anyway, they're all variations on the same. Which okay, everybody raise your right hand. Repeat after me. No, I'm just checking. Yeah, I'm just checking to make, okay, good, you're all good. I've watched during exams right-handed dominant students, okay, they're doing the exams, they get to a right-hand rule where they need to use a right-hand rule, and guess what they do? They use their left hand. They're writing, right? I have to go over, I have to tap them on the shoulder, I have to whisper in their ear, "You just used your left hand." And they look at me like I am nuts. I'm like, "No, I didn't." I was like, so, lefties, left-handed people, rejoice. You get so much garbage from this right-handed world, right? This is your one time to shine. Because guess what you get to do?
The one time. Just kidding.
Yeah. Try using scissors or a mouse as a left-handed person. All right. So let's practice. Here is a magnetic field. So there's the magnetic field. Here is the velocity. What direction is the force? Don't say it out loud. Just do the right hand rule.
No, you gotta use both hands now.
No, not both hands. Just try it. Okay. What are you going to do? You're going to handshake what direction first? Velocity. So we're going to point our fingers to the left, right? Okay. Now that we've got our handshake direction established, there needs to be some sort of rotation to make sure that our fingers, when we push them at like 90 degrees, point which way? Into the screen. You see how the magnetic field is indicated into? So which way is the thumb now pointing? Down. Which way is the bee going? What does it say? Do you see a bunch of X's or a bunch of dots? No. I drew it in green. All the X's are... Yes, the green thing. No, I told you no. All right. Give me a direction. Up, down, left, right, and out. In. We just did in. Out. Give me a color. Blue, black, or green? Black? Okay. The velocity is headed out of the screen. The magnetic field is pointed up. Find the direction of the force. Do you have enough dexterity to... Is your cast okay? You can rotate your body. Oh, you got your left hand going. Yeah, look at you. Ramsey wins. Do you mouse with your right hand?
I go right hand. I also kick with my right.
Yeah.
When I eat,
Yeah.
You have like a full. Oh yeah. No.
Okay. Which way do your fingers go? Out. Okay. It's easy for me because I'm standing up here at the front. But if you're sitting this way, you can either like try to hold it like this, or you can just like go like. It helps sometimes to just turn your body. Okay. During the exam, do not turn your body. Don't turn around. Whap. Yeah. Try to keep your right hands to yourself on the exam. And no cheating with the, your physics gang signs. Okay, so you're going to turn your hands are going to come out. Which way is the magnetic field? Got to rotate so your fingers can go up. Which way is your thumb sticking? Yeah, into my ear. Okay. But I got to do this on the screen this way, that way. Okay. So the force is that way. All right. Let's see. Let's do. What haven't we done yet? We did forwarded. Let's do. Okay. So this is going to be a little bit different. The force on a particle that's moving to the right is directed upwards. What direction is the magnetic field pointed?
For that to be
So remember, right-hand rule follows direction, the vectors, the order of vectors, right? It's V cross B, but here you don't know B. What do you know? You know the force has to be up, right? What else do you know? Your velocity has to be to the right. So your fingers would naturally bend which way? Into the screen. So you can use the right-hand rule and you can do it backwards, out of order, as long as you get the pieces parts. Right, as long as you have two pieces of information. Okay? All right. So that's how we're going to visualize and draw pictures into and out of the page, dots and X's, that sort of thing. Back to here. Let's talk units for a second. If your V is perpendicular to your B, what's the angle between them? 90 degrees. And that means QVB sine 90 is equal to what? Guess the other one. QVB. Sine of 90 is 1, right? Okay. So a lot of times you'll see the magnetic force law just written as QVB. What is the implied relationship here? If you don't see the cross product and it just says QVB, what are they implying? We have a perpendicular velocity in magnetic field. Okay? So you'll sometimes see the magnitude written like this without its angle on it. It just means that V and B are perpendicular to each other. Okay, but this lets us kind of suss out what the units are here, right? This is force divided by charge and velocity, right? What are the units of force? Newton. What are the units of charge? Coulombs. What are the units of velocity? Meters per second. That's called a Tesla. After Nikolai Tesla. A brilliant but very sad story. So if you get a chance to look up the story of Nikolai Tesla, I'm not kidding, okay? The brilliance of this man cannot be understated. He's definitely up there with like Einstein in terms of his abilities. Died alone in New York City, in love with, and he thought married to a pigeon. I know it sounds funny, but his mental disorder was extreme. And he was taken advantage of by the robber barons, the Westinghouses and the Edisons of the time. He invented our electrical grid, everything we know about AC circuits and all that kind of stuff. Absolutely incredible mind. And unfortunately taken advantage of because of his fragile mental state. But we honor him with the unit of the magnetic field. And I hope you can see at this point that you should just give up on units. Right? Not that they're not important, but like, what are you always going to measure magnetic fields in? Teslas. And so if it says milliteslas, what are you going to do? Just going to standardize, right? I've been harping on you the whole time. You really want to do it here, okay? Because breaking down a Newton and a meter per second and oh my gosh, it becomes crazy. What's a Coulomb per second, by the way? It's an amp, right? So this is a Newton amp meter, whatever that means, right? But it is the units of magnetic field. I should say that this extends a little bit, but I really don't want to get into that until next time. Just to dot some I's and cross some T's here for you. Two different ways here of finding cross products. This top one does return a vector. This one returns a vector magnitude. And how do you figure out the direction if you're using this bottom one? That gives you the magnitude. So how do you find direction? This is where you use the right-hand rule. Okay? And remember, right-hand rule always means you got to do it in order. You're going to for A cross B, which way do you handshake? A. Whatever direction A is going is the handshake. And then you cross it into B by bending your fingers, right, at 90 degrees. What if it's not exactly 90 degrees, right? What if you've got like, I don't know, vectors that are like this? Oh, that's not a B, that's an A. Right? And it's not a 90-degree angle between them. You can still do the right-hand rule. You still go A, and then you have to rotate your hand around so that your fingers can point in the direction of B. You see here how I'm not like going full 90? I'm just kind of rotating in the direction of the angle theta up to B, right? And my thumb, no matter what, no matter if it's perpendicular or a portion of it, my thumb still points which way? Out of the screen, right? For those of you that are reviewing this on YouTube or seeing it for the first, well, boy, if you're seeing it for the first time on YouTube, good luck, right? Because I can't show you the right-hand rule. But if you're reviewing it, right, try to remember what you were doing here in class, right, with the directions of things. Magnetic force as opposed to electric force. Because guess what we're going to do next chapter? Maybe is it this chapter? No, I think it's next. I don't know. I can't remember what chapter. It all blurs together for me. All right. So we're going to leave it there. Next time we're going to come together. We're going to talk about current and magnetic fields, because if a single charge experiences a force, a whole bunch of charges are going to experience a force. There will be integrals. There will be torques. And there might be some cocaine.
Oh, I gotta come.
See you then.